few equations, there are a few, but I mostly show pictures. So hopefully they're a little easier to follow after lunch. Yeah, experimental constraints, and very briefly, an outline here. It looks like I'll jump around a little bit, but these are the topics that I'll go through, and I'll spend most of the time on microstructural observations. What can we actually say about the melt distribution at the grain scale? And then key effect of grain growth on melt distribution. Wetness measurements that we do that then link into what Yasuko Takai showed this morning directly, the Takai-Holtzman theory of how you can apply the wetness that we measure to calculate, for example, viscosity. And then back experimentally, seismic property, we do direct measurements of seismic properties as well. I'll mention those very briefly, as well as rheology, very briefly, some deformation experiments. Brief look also at grain boundaries. That's also something that is very dear to us in all of this. This is all behind. There was a discussion this morning already in terms of the relative importance of grain boundaries versus melt in terms of diffusion and flux. And then the last part, this is work that we've been doing recently, trying to link, that's an attempt to link the experimental observations directly to observations of natural rocks. So we'll see how that goes. Motivation, of course, I don't need to say too much, except that it's really interesting how much melt is in the mantle is, of course, one of the questions we're trying to answer. And answers come from other people, seismologists, for example, who say there are a few percent, and they base that on images such as these. What is plotted here is Q, so attenuation of seismic waves, in particular here in a back arc in the Marianas, and then a few others, so Central America, Nicaragua, and Costa Rica. And the observed Qs here are very low. So Q of 34, that's very low. So an elastic solid would have Q of thousands or tens of thousands. This is very low Q, meaning the seismic waves get attenuated quite heavily. And the important part is also from work, this is by Jeff Abers, was the first author on this, but Doug Wiens has done a lot of work there in the Marianas. They find the lowest velocities beneath the back arc. And that's important because, of course, you could have in the subduction zone contributions from water as well as from melt. But they're arguing basically what's shown here is, again, QS, so shear Q. These are parameterization. This is work that we've done on olivine, direct measurements of melt-free olivine, and work by McCarthy and Takai as well, that basically says that the Qs that you'd predict at that depth for a given temperature, that you can calculate grain size and a certain pressure, this is for just contribution due to temperature, and you don't get the observed Qs. So the observed Qs are much lower than you can predict solely based on temperature. The argument is that the arc is over here, the lowest Qs are over here, so most likely what you're seeing here is melt. And that's often interpreted as a few percent of melt, so very loosely. And similarly, electrical conductivity measurements, the melt experiment at the East Pacific Rise had much lower station spacing, so had much lower resolution in comparison to these experiments here at the back arc. So at the top here, these are seismic stations, so they're quite dense. The melt experiment didn't have the dense station spacing, so this is electrical conductivity. And the low resistivity that they observe here between 1 and 10 ohm meters, again, they interpret that based on laboratory measurements of the effect of melt on olivine and so on, of a few percent of melt up to 10% of melt. And then the contrast is, of course, these uranium series models, and one of the co-authors of this paper here is here in the room, Ann McKenzie. These are interpreted typically as indicating that there's 0.1% or less. So it's an order of magnitude at least lower that's inferred of melt in the mantle. Essentially, so that gets interesting in terms of nominally melt-free deformation experiments, they're up to 1%. So the inference is that in the mantle we have 0.1% of melt according to these models. So looking at this, of course, it starts at the grain scale. Melting starts at the grain scale, so that's where we have to start with all of these models and experiments, looking at what the grain scale melt distribution is. And the earliest work for mantle rocks, aside from material science, this is a model adapted from material science essentially, is that the distribution of melt, and that contrasts with, for example, the porosity in the sandstone, right? That's important. The distribution of melt is controlled by surface tensions. So the tensions between grain 1 and melt and grain 2 and melt, these tensions here are balanced by the tension along the grain boundary. And that sets up the dihedral angle that was discussed, and I'll discuss that extensively today, the dihedral angle between these grains and the melt. And in 3 dimensions then, this is from Bargan and Waff in '86, the 3-dimensional melt distribution then is perfectly interconnected in this 3-dimensional network. The key assumptions though, and that's what I'll discuss today, is that in this idealized model, one is that you have crystalline isotropy, which is sort of a contradiction in terms. Crystalline grains are by definition anisotropic. Uniform grain shapes that are space filling. Single grain size, of course, for the space filling. It's a static model. Nothing changes in this model, and it's self-similar in the sense that you can change grain size or melt fraction, and the model looks exactly the same. Right? These are very stringent assumptions. I'll show how they sort of collide with what we see experimentally. So the earliest work on this, again, Waff and Bilal in '79, experiments in a piston cylinder, I think at 1 gigapascal or so, and then they took light microscope images. So, you know, for the first work, right? So, and in order to interpret this light microscope image, here's the drawing that goes with it in order to interpret this here. The measured dihedral angle, right, the contact angle between 2 crystals in the melt, is about 47 degrees, right? So jumping right in, this is then, if I paraphrase Dave Kolstad from yesterday, the sub-frog eyes view, I guess that's transmission electron microscopy. So the scale here, 500 nanometers and 20 nanometers. We find these structures, right? So if you go back in this model, right, that's that green cross-section here, that's what we're imaging. So, you know, we find structures like this. But the thing to note here is that, of course, the dihedral angle at that high resolution, well, of course, the dihedral angle that we measure at this high resolution is much, much less than 47 degrees. In fact, in this paper here, the measured dihedral angle is something like 10 degrees. Okay? So it's much smaller dihedral angle, and I'll come back to that over and over again. These are really small dihedral angle here if you have the resolution. And I'll come back to this image as well. Oops. So the importance of resolution here, that's from a paper by Wark et al., and there is a controversy whether wetted grain boundaries exist. So the dihedral angle model, if you go back to the idealized isotropic model, for a finite dihedral angle that's greater than 0 degrees, the grain boundaries are not wetted, right? The melt is in these triple junctions. And we published papers saying that, no, we do have wetted grain boundaries, and this was basically arguing that what we're calling wetted grain boundaries are just these triple junctions sectioned along axis. And as you know, for the modeling that was done in this paper, images like these were used. So the point here is the experiments that I'll show, the experiments look the same, right? So it's really more a way of looking at them, you know, at what resolution do you take your images at. This is from Rishino et al., and coming back to this, so, you know, if you measure dihedral angle in these kind of images, you get relatively large dihedral angles, right? But again, it's a question of resolution, the same here, and these are directly copied from the papers, of course. The dihedral angle here was quoted as 34 degrees, but that's a problem of resolution. So I'll step through this. This is from one of our own papers. Similar resolution here, a scanning electron microscope image, I should say, for those not used to looking at them. So, oops, the melt in all of these images is the bright phase, the darker grays, the olivine, and then you can see in all of these images, these are cracks that were discussed yesterday already. These are quench cracks, basically. When you cool, the way these samples are made, they're equilibrated at pressure and temperature in a piston cylinder at 10 kilobars or 1 gigapascal. And we want to preserve the structure, of course, at high temperature. So at the end of the experiment, we just turn off the power. And the temperature in the first second drops about 200 degrees C, and the pressure correspondingly drops. And that's when you get these cracks here forming throughout. And it's actually, yeah, these are due to the thermal expansion anisotropy of olivine. So olivine is anisotropic in all properties. One of them is thermal expansion, and that produces these cracks. This is all olivine. Yes, I'll show later somewhere. There's a bit of OPX here, but other than that, it's all olivine. Yeah. So going through this now, that's the same image at the previous resolution, and it looks like you don't really have wetted grain boundaries. The melt distribution is heterogeneous. I'll come to that. But the interesting part is if you go in at high resolution now and look at particular features here, and that's this area here in the white rectangle blown up. And if you measure here, you could say there's some relatively large dihedral angles, but it's very clear, if you go up in magnification, the dihedral angle here, and I'll actually advance to the next one. So it does look like it actually is not a zero dihedral angle. It's not a wetted grain boundary. Somewhere here, the boundaries actually melt free. But anyway, the angle is something like 1 degree or something like that. And similarly here, that's very characteristic. Basically, you can see that this is a facet. So the olivine, because it's anisotropic, if you take a single grain olivine, it has a nice habit, right? If you go in a mineral show, the minerals have nice surface. That's what the beauty of the mineral is, the surface morphology. And when you have space in these partial molten aggregates, you tend to develop the same kind of morphology. So you have faceted crystal melt interfaces, and that leads to these very irregular looking geometries here. So the same thing, so here, if you go back, right, that looks like a triple junction surrounded by melt-free grain boundaries. You go in at the appropriate resolution, and it's very clear that's not a melt-free grain boundary. And a melt-free grain boundary is here and here, and I speak, saying that these are melt-free. I'll come back to that. I'll show grain boundary images. But we've looked at these, of course, also with the TEM. So these are melt-free at the TEM scale, right? So it's not a question of you could go to higher and higher resolution. At some point, all grain boundaries are wetted. That's not the case. They're certainly melt-free grain boundaries, and they're wetted grain boundaries. But these layers here on two grain boundaries, on grain boundaries, they're about 100 nanometers or so wide. You can see that easily with the field emission SEM. So today, with the field emission SEM, it's very straightforward to produce these images. And another triple junction, another wetted grain boundary, again, so 0 degree, so that the dihedral angle here is 0. It's a wetted grain boundary. The dihedral angle here is very small, less than 10 degrees, and then you have something that's perhaps a bit larger than 10 degrees, right? So one last set of images here, that's sort of similar. Yeah, the square here, again, not particularly high resolution even. You can see that the grain boundary that appears melt-free here is clearly wetted by melt. And again, you have melt-free grain boundaries. So, but again, if you look at these details here, the dihedral angle is small, right? So the point is, if you want to measure dihedral angle or you want to measure wetness, as I'll come back to later, you need sufficient resolution in order to see the melt geometry. This resolution here at this scale is not really sufficient.
So is the figures you've been showing, that generally where you zoomed in and say surprise, it's different than when you think it's on the micron scale. Is that basically what you recommend?
Yeah, so essentially these layers are, so if you go back to the triple junctions here, oops, yeah, of course, right, so these layers here, they're about 100 nanometers. So you have to have sufficient resolution basically in order to see something that's 150 to 100 nanometers. So with the field emission SEM, it's no problem. The problem is, and that's where the TM becomes also a problem, is that if you want to have a representative volume, right, this for modeling, that becomes a task, because you have to image at a resolution where you can see these things, large enough area so that it's representative, right? So that's the challenge really, more than being able to resolve this with the field emission SEM these days.
It looks as if all the triple junctions have melt on them. Is that correct?
No, you mean that all the triple junctions have at least one wetted grain boundaries? No.
All the triple junctions have melt.
Oh yeah. Yes, I'll come back to that. Again, yes, that's yeah. So okay, stepping through, right? So, comparisons, we can say, the experiments, as I said, are the same. There's no difference. It's just the question of what resolution do you go in, and it's very clear to me that there's a wetted grain boundary here. If you just look at it at the appropriate resolution, you'll see that, and probably more. There's wetted grain boundaries all throughout this. Just, as I said, the experiments all look the same, at the scale, so I assume they're also the same at the micron scale, at the, one scale of a micron or submicron. So another example here, I'll come back to this one. Again, a blow up here, a wetted grain boundary. The white dots indicate melt-free grain boundaries. And everywhere where you see this double arrow, that's a wetted grain boundary. So that, we have taken high resolution images in all of these, and everywhere where there's a double arrow, there's a wetted grain boundary in this aggregate, right? So they are numerous, and as I said, I'll come back to that.
Can we go back to that?
Yes?
So I'm wondering how you distinguish wetted grain boundaries because they're free versus grain-grain contacts with melt. And I'm particularly looking at the vertical arrow in the upper left corner.
The vertical arrow, this one here.
Yeah, I mean, it looks like there's a finite sized gap between.
Right.
Which
Yeah,
is
so that's
a little bit different than grain-grain contacts where you have this little bit of melt on the surface, no?
You mean different than this here?
Yeah.
Yeah, it's related. So, I'll try to come back and explain what we're seeing here, why we have this difference between, the idealized model and what we're actually seeing in these experiments. One thing to note here is a little bit that this grain tends to be faceted, right? Whereas, you can't really clearly make out facets here. So there is that problem. So there will be two things. One is grain growth, the other one is faceting. Faceting, if you look at these larger pockets, they're surrounded typically by olivine grains that have faceted grain boundaries. So the faceted grain boundaries, if you look at grain growth theories, they're slow growing, and they tend to stabilize these larger melt pockets. But I'll get back to that a little bit.
Can I interject again? Sorry.
Yep.
How do you know that these are fully wetted boundaries? Because it's a three-dimensional problem, right?
So I'll get back to that as well.
Okay.
Right?
Okay. Right.
Yeah, so yes, exactly. So connectivity size of triple junctions, and that's work, of course, by Wenlu Zhu that she showed yesterday. And in particular, right, so, a little bit the background in the introduction, do you have, a fraction of a percent, do you have percent level? And at the resolution here, 2%, it looks like the melt is becoming disconnected. And there was yesterday a little bit the discussion of a percolation threshold. When Lu analyzed the connectivity here, and at the 2%, the coordination number, so, if you look at the nodes here, the coordination number is peaked at 1. Whereas if you look at this idealized model, your connectivity, of course, at the grain corner should be 4, right? You have 4 triple junctions coming together to form this node. So it should be peaked at this coordination number of 4. And that's, again, a problem of resolution, of course. So triple junction size at 4%, all of these are triple junctions here. So there is a triple junction, I'll come back to that more, but there is a triple junction at every grain corner. But most of these triple junctions are very small. They're micron sized. And again, in comparison to these larger pockets that are surrounded by these facets, right? These are much larger. And we've analyzed this, so at 0.6% melt, right? Because we want to know what happens at low melt fraction. At 0.6% melt, a grain size comparable to, I think, Wenlu's samples. And you can see basically what's plotted here is the total number of pockets. So just counting, so at 0.6%, the pockets are all isolated in the image, in the 2D image. So no problem counting them. So the percent of the total number of pockets versus the total number of melt area. And you can see that most of the melt by area is contained in a few of the largest pockets, right? So these are sizes in micron. The size ranges are chosen somewhat arbitrarily, although that's an interesting distribution here. So size range in micron, basically, it's what we're saying here, right? You have one of these large pockets that has much more melt in it than all of the triple junctions, right? So basically, that's what we're quantifying here at a lower melt fraction. And it becomes interesting, of course, looking at these size ranges. So I've lumped everything together here. These are all the melt pockets, triple junctions mostly, that have a size of 1.4 micron or less. And you can see that's 70% of the pockets that contain only 15% of the total of 0.6%, right? So that's 0.6% is the total melt area. 70% contain only roughly 15% of that total here. And of course, the 1.4 micron, if you say that you need 2 voxels in the microtomography to resolve a triple junction, then you would not resolve here the majority of the triple junction, basically the melt is disconnected, right? You lose the connectivity at some point. And that's essentially, these at 2%, right? That's the network is no longer fully interconnected, right? So it's a problem. And so going back a little bit to the percolation threshold idea, that's something that I published a while ago. And this looks very radical. So the relationships here that were discussed yesterday, this simple permeability as a function of grain size and porosity, right? These are these straight lines just with different parameters here. What I was saying at that time is that somewhere at a melt content between 1 and 2%, you have a fairly dramatic reduction in permeability. And that's essentially the combination of this analysis and the tomography at some melt fraction here. The connectivity, that the size of the tubules is large enough, you start to fall on this regular permeability law, but somewhere at a smaller melt fraction, you have a fairly drastic reduction in permeability because most of the triple junction tubes are just very small, right? And you don't have enough of these large ones anymore to make a good interconnection to have high conductances of your individual melt pockets.
I just want to make one clarification. That's at the 2%, yes, we do see some of the disconnection, but when you run the model, right, you do also have at least one cluster that's connected from top to bottom, and this is also size independent. So
right.
I'm not sure after 1%.
Right.
Okay.
So so that's what I'm basically. So that's what I'm saying, that at some point, at some melt fraction, a little less than 2%, or somewhere around 1%.
Below 1%, I cannot say, but
Yep.
There is about 1%. We all have all of our model. When you run permeability through this, right, without just reproducing this, they still have permeability.
Okay. Yep. So that's essentially this idea. The question is where this fairly rapid drop occurs. The key point I want to make, though, is that it's not a percolation threshold as was discussed yesterday. It's not an absolute cutoff of connectivity. So this is an SEM image, TEM image that I showed earlier on. So at a melt fraction of 0.01%, John Fitzgerald at the time at ANU went around and looked at 40 of these triple junctions by TEM, which is very painstaking. And 39 of them had melt on it. So that's the scale bar here, 20 nanometers. So the melt is interconnected at basically all melt fractions that we've ever done experiments at. The key point is that these laws can't be extrapolated to this kind of, in my opinion, can't be extrapolated to this kind of melt fraction, right? Because the melt distribution also becomes heterogeneous, and the triple junctions that are making the interconnection are much smaller relative to the absolute melt fraction. Essentially, that's.
Are you going to say anything about whether those little melt things are faceted or not? I don't want to upset your.
No. There is so this one is of course the perfect, poster child. But we have images where there is faceting. I think I'll show one of these. There is some faceting going on, but at that scale, it doesn't really make a difference, right? The triple junctions, more or less are triangular, and then you often see that, if one of the grains is faceted, you have a very small dihedral angle. But
it makes a difference to the distribution, right? Just because if the solid grains are isotropic, then all those triple junctions are going to look like that.
Yeah, they don't.
And you're not going to get channel flow. Whereas if they all look like that, then actually the simple-minded percolation will be correct.
Yeah, except that, right, the background is that, this is important, right? So even at 0.6%, right, the size of the triple junction is not uniform, right? The size varies, right? This is what is shown here, that, even at 0.6, you have a and I'll show that sample later on.
6 to me is large.
Right.
Well, so I'm interested in what happens at 0.1.
Well, okay.
As you said,
as I said, it becomes very difficult, but okay. At least at these kind of grain sizes, I'll show that later on. The problem is that you always have a few of these pockets, and I'll show the reason why. Hope to get through all of this. But so, okay, let's go back to that discussion perhaps at the end. All right, so wetted grain boundaries. So this was the question I think that you asked, Lars. How do we know that we have wetted grain boundaries and not just, instead of a cross section, a long section? And we did, this was work with one of my former students, Gordon Agarpage. We did serial sectioning since, we needed the resolution of at a scale of 100 nanometers. We did serial sectioning, and I won't go into all the details. We're not going to do very many of these. It's painful work and a lot of work for each sample. We have, I think, something like 20 sections or so. You can see 4 of them here. The sections are about 1 micron apart or so. Of course, that's our vertical resolution, right? But it couldn't bear to do closer spaced sections. The key, what you can see here, so here's an olivine grain, and you can see very faintly that there's an included orthopyroxene grain. So that's sort of a marker. You can see that orthopyroxene grain throughout here. What you can see is that at the bottom here, you have some of these large pockets. And if you go through here, right, that's so the depth from the original surface, that's down 16.5 microns. Here's 12 microns, so a little shallower. You can see these large pockets change very rapidly, and that was stated by Wark et al. In their paper. That's what they observed. But these wetted grain boundaries, which they didn't resolve in their work, these persist throughout these sections. You can see that, and everywhere where there's an arrow, there's a wetted grain boundary. In particular, this one here, right? You can follow this through, essentially the grain size here of this grain in the middle, right? So that is, clear evidence. If you look at the size of these triple junctions, and the size of the sections that are stacked up here, these are really wetted grain boundaries. That's not just a sectioning effect, right? That was the main point. And if we do this in 3 dimensions, that's the image that we got, which is not perfect. You can see these are wetted grain bound. That's basically a grain cast here. If you look at this, that's a very large grain that was in the area that we imaged. We imaged all of it at high resolution. You can see this ribbing here is not real, of course. That's a problem where we didn't align the sections perfectly. There's lots of things that I know now how to do better if I ever did that again. One of the things is we drilled laser holes to basically measure the depth by white light interferometry, how much we took off, because there is a bit of variation even though we kept the polishing procedure the same. So we needed to know how much we took off, but then also to rectify the image, actually more important. And so we should have done that a little differently. But anyway, so this is a smooth surface, right? You can see that in 2D there's none of that drilling going on. That's an artifact of these individual layers here being slightly misaligned. It's not trivial actually to reconstruct that in 3 dimensions. That's what she did. So that's a 3-dimensional view, and you can see that a lot of the grain bound. So of course at some point this becomes completely opaque, so it's a little bit misleading, right? We measured the wetness in this and then quantified, as a fraction of wetted versus melt-free grain boundaries. But basically, in 3D, quite a large number of grain boundaries are wetted by melt at this melt fraction. So that's a large melt fraction, of course, but yeah, at this melt fraction, we have quite a number of grain boundaries wetted by melt. And, again, there is the resolution problem. So if we take a little section out of this, erode it down to 700 nanometers, then that starts to look very similar to the X-ray microthermography, where of course you can't resolve 100 nanometer wide layers on the grain boundaries. So the key part, why are these observations so different from the model, right? And we have to explain the size range, the large pocket, and the wetted grain boundaries. And the answer is, I'll show later on, it's not just the anisotropy, but also that the system is not static. The system is dynamic. There's continuous grain growth, and of course grain growth is driven by exactly the same surface energy that also determines the local melt geometry, right? So it's a competition between the rearrangement on the aggregate, or the upper mantle scale due to grain growth, and the local geometry trying to form an equilibrium dihedral angle, right? And these are grain size distributions here. That's from the earlier paper, normalized distribution. So, but you can plot that also as absolute scale. You get a log normal distribution. So from Lars's work. So just basically anytime you measure grain size, you come up with a grain size distribution. So it's not one single grain size. And moreover, as I said, it's not static, right? So as time goes on, you have grain growth. And the best view of this, so grain growth, how does that affect melt distribution? The best view of this is observation in analog material some time ago now, was done by Nico Walte and Paul Bons in University of Tübingen on this analog system where you can watch it directly on a light microscope, right? In the piston cylinders, we have snapshots. We can't watch the stuff. But here you can watch it directly. And I'll play these movies a few times. It's quite interesting, right? So this is a time lapse. That's 200 hours or so, taking a snapshot every so often. And you can see that. So the arrow here, the red arrow, indicates a grain that initially is not particularly large, but over time, is the largest grain in this area. And you can see the melt moves around. You have these transiently wetted grain boundaries. If you wait long enough, right, the grains grow it shut again, but it's a dynamic system. So, if you watch this in one place, you have a wetted grain boundary, it eventually disappears, you have a wetted grain boundary, this grain now shrinks and disappears, right? So the neighbors constantly have to readjust, right? There's nothing static about this. The neighbors constantly have to readjust to new neighbors because grains disappear, and you can see the small grains disappear. So that the grain boundaries, when they first get in contact, are not in their minimum energy configuration. They have to adjust to that first. But the problem is it's an ongoing process, so you're never done, right? So while a wetted grain boundary disappears in one place, you have another one reappearing in another place.
Is it a comparable timescale for the olivine?
No, the grain growth rates, you have to measure that. And olivine doesn't grow that quickly, right? So this is 200 micron here. This grows larger in this analog system. If you put olivine at 1800 degrees or something like that, 1700 degrees, you might get grain growth rates that are comparable. So it's a temperature activated process grain growth, just like diffusion. Basically, it's diffusion in the end, as an exponential temperature dependence.
So but then if you look at this, right, it seemed to me that the faceting at the beginning you see start to disappear.
That's an interesting point, so I'll come back to that. Yeah.
And when you talk about the wetted boundary, a lot of them are related to faceting. So then that's like, in the experiments, you can cook it for a month, but in Earth, you have...
No, it's actually the opposite, so I'll show that a little bit. One is that this system here is less anisotropic, so the norcamphor as a solid is less anisotropic than the olivine, so the grains appear more rounded. But in the olivine, you actually get more faceting at small grain sizes and less faceting at larger grain sizes. And again, you have to establish, the facet is a slow-growing minimum energy surface, right? So it's slow-growing, right? So, in order to establish a facet, you can do that more easily on a small grain rather than on a large grain, which, if you look at this large grain, right, it has any number of neighbors. It's not just one neighbor that it has to adjust its grain surface to, but there is any number of neighbors. So I'll show you pictures at a range of grain sizes in olivine that shows that the faceting is more pronounced at small grain sizes and less at larger grain sizes. Yeah?
Lee, are these two-dimensional structures? Is that right?
These are essentially two-dimensional structures, yeah. So here's another movie just at a single grain that shrinks and disappears in the middle. And you get wetted grain boundaries, everything, all the neighbors constantly have to change, right? You can see that, this pinching off, the grains become very odd-shaped and then have to, pull back to their preferred habit. They want to establish their preferred faceted habit. The problem is, though, if you have a neighbor, right, you can't establish necessarily a facet. You can establish the facet for the olivine system where you have melt next to you, right? But the neighbor, of course, wants to establish their own, so that the minimum energy grain boundary plane orientation is necessarily complex in a system as anisotropic as olivine.
So is this a thermodynamically controlled problem or a kinetically controlled problem?
It's grain growth. So in some sense, you have kinetics locally. Overall, thermodynamically, of course, you have grain growth that drives all of this. Right?
Yeah,
So locally...
You can say anything about pinning?
I mean, if you put second phase in, then the grain growth rate slows down. So pinning, it comes from material science where you want to engineer certain materials to certain grain sizes on a time scale, right? In the Earth, pinning is means that the growth rate is slower, but you still have grain growth. And if you talk about
You've got in the Earth you've said you've got a four-phase system, so you're going to get a lot of thinning, which gives you longer to establish these things I would have thought. Because it's competition between two things.
right, but then you have to take interface boundaries into account. So yes, grain growth rates, the growth rates will be slower for sure, which you might complicate. So when Lou showed a little bit of that, the melt distribution then becomes even less homogeneous. So, all right, I wanted to get a few other things. Dihedral angle, indicative, but you can't characterize the whole melt distribution. So again, TM scale, so that's maybe something, you always, quite frequently, not always, but you quite frequently, so you can see faceting here at the, nanometer scale. And again, you can measure dihedral angle, it's very large, or you can measure the dihedral angle here. Another point I'd like to make is that, melt in that sense is a very sensitive indicator of surface energies. Here's the subgrain boundaries. In the TM image, you can see the individual dislocations here, and the dihedral angle here is large. So meaning the subgrain boundary has a much lower surface energy than the grain boundaries here. And that's, throughout, there's another subgrain boundary here. So that the melt, as I said, is an indicator of grain boundary energy in this system. So instead of dihedral angle, we measure wetness, of course. Yasuko Takai introduced this. So the ratio of wetted and melt-free grain boundaries, and you can calculate, we can both measure that, and you can calculate it from the idealized model. So I'll compare this. So here's a little bit of that. So 0.6%, that was the sample where I had the distribution of sizes. So there's, you can barely see it, but that's a larger pocket. There are a few larger pockets, right? These larger pockets contain most of the melt, but then what you can't really see anymore at this scale is there's triple junctions everywhere, right? And these small triple junctions at a size of a micron or so, they provide the interconnectedness. So this is all interconnected along 3 grain edges. But the melt distribution still is not homogeneous, still does not look like the idealized model, because you have a few of these which are due to grain growth. So these samples are run for 2 weeks at 1350 degrees C in this case. So we start out, the powder that we start with is about a micron or less. So now we have a mean grain size, in this case, of 31 microns. So we have lots of grain growth in these samples. That's why we start with this very small grain size initially, in order to get to a steady state that when Lou mentioned yesterday. So we want to get to a steady state grain size distribution that is steady state growth. Not static, but steady state in terms of the normalized grain size distribution have a certain shape, a log normal distribution. So going up in melt fraction, 0.6, 1.7, 4.1, and then this was the largest, highest melt fraction. You can see that wetted grain boundaries become more numerous as you increase in melt fraction. And the point that we're discussing earlier, so that's 3%, but a grain size now of 8.3 micron. And you can see, and that's something that I noticed, I'll show some pictures later on. I noticed early on that if you have these really fine-grained aggregates, they look much more faceted. And actually, if you go in with the TM even, there are barely any wetted grain boundaries. So the wetted grain boundaries appear as you go to larger and larger grain sizes. So, the small grains can more easily express the habit than the large grains, which, it takes longer and longer for the large grains to establish all the orientation relationships with their neighbors and towards the melt. So wetness is a function of melt fraction and grain size, color-coded by grain size here, less than 20 micron, more than 30 micron. Melt fraction here versus wetness. The curves are those calculated for the idealized model and for dihedral angles of 30, 10, and 1 degree. And you'll find that for fine-grained materials, you have a larger dihedral angle. We directly measured dihedral angles. And then the coarser you get, the higher the wetness becomes. And the wetness then exceeds that calculated by the idealized model for a dihedral angle of 1 degree. So you just have wetted grain boundaries that are not accounted for in the idealized model. And interesting, so that's the dihedral angle, and wetness is a function of temperature. So there is no temperature dependence, right? So as long as you account for, so this is at 2% melt, as long as you account for grain size, so here's 8.6, here's 25 micron, the dihedral angle at 8.6 is near 30 degrees. If you go to 25 micron, it's somewhere near 10 degrees, right? And that goes with the wetness, right? That's, exactly the same thing. So the grain size dependence here of the wetness. Fine-grained materials have a lower wetness. Their pockets are more isometric. At these coarser grain sizes, you have more wetted grain boundaries. And here on the left, the grain size dependence, even if you keep the melt content fixed, right? That's the same thing again. As grain size increases, wetness increased at near constant, not exactly constant, but at near constant, so 2 melt fraction ranges here. So if you take all of this into account, then there is no temperature dependence of grain size, of wetness or dihedral angle. An interesting part, the comparison, again with an analog system, borneol diphenylamine, from Yasuko Takai's work. So here on the left is the data. That's now the gray dots here, and the borneol and diphenylamine is plotted as a function of temperature. At the lowest temperature, it falls on this 15-degree dihedral angle line, although I think the measured dihedral angle is somewhat larger. But then at higher temperatures, the wetness is similar to the olivine basalt system. I'll show some microstructures that Yasuko gave to me to show the difference in the melt distribution here. One interesting aspect that, yesterday when I saw Dave Kolstad's talk, the idealized model predicts that you go to a wetness of 1, so disaggregation, all grain boundaries become wetted, and that's clearly not the case here. So the data, ours doesn't extend to this high melt fraction, but these data here show that, the wetness stays less than 1, and that's actually beautifully shown here. You have a very high melt fraction, but the olivine grains tend to form little clusters. And that's essentially, as you have wetted grain boundaries that can lower their energy by having melt on them, at least transiently, you also have grain boundaries that really want to stick together, even though you have plenty of space for them to be apart. So that's, essentially shown here. Disaggregation isn't complete, at least at these kind of, 20% melt. Instead, you form these clusters of low surface energy. Briefly, seismic properties. We do direct experiments, so we measure at seismic periods in a modified Patterson apparatus, so similar machine that Dave Kolstad was talking about yesterday. We measure up to 1300 degrees. The confining pressure is really there to keep the interfaces tight, to compress them, not so much. This is relatively low, 2 kilobars, relatively low pressure for the Earth. So we measure shear modulus and attenuation that I mentioned earlier. Attenuation is energy loss per cycle. We can clearly see an effect of melt on the shear modulus as well. So the shear modulus is reduced. Yasuko talked about that. So melt free versus melt bearing at, trying to keep everything else, so temperature in this particular example the same. But the interesting part is also dissipation, attenuation, left melt free. Right, so there is clearly a temperature dependence, right? So we have viscous, anelastic behavior, to be precise, not viscous, but anelastic behavior. That's the absorption band. I can't explain the details. But there's a temperature dependence, and then there's a frequency dependence as a function of temperature as well. What I wanted to point out is if you compare melt-free and melt-bearing, you clearly get a different behavior. You have this high temperature background that's similar to here, so a constant slope as a function of period. But here, in this temperature range, you have clearly different behavior. That's an absorption peak, so energy is absorbed at a particular, so in this temperature period space, at a combination of temperature and period. And the model for this is melt squirt. So that goes back for quite a ways now, that essentially, due to the applied shear stress, you move the melt from one orientation into another orientation. And the time scale of that movement depends on the viscosity of the melt and the aspect ratio. So, the throat that you have to squeeze the melt through. And the triple junctions have aspect ratios in this parameterizations that are 10 to the minus 1, so 0.1 to 0.01, whereas these wetted grain boundaries have aspect ratios of 10 to the minus 4 or so. So we're arguing basically that, it's the wetted grain boundaries that essentially is causing, so we have an enhanced high temperature background, and in addition, this absorption peak that's caused by the melt squirt due to these low aspect ratios, these wetted grain boundaries. So, and that's why I talked to Yasuko. So in the analog system, borneol diphenylamine at 48 degrees, they don't see that, although it's just at one temperature. you clearly see this peak much better if you have a range of temperatures that you can step through. But they don't see that, and an explanation might be that at 47 degrees here, that's the system that has a wetness that sort of corresponds to the isotropic, most closely to the idealized isotropic model. So that's on the left here. Whereas at the higher temperatures, so 62 degrees here, you start to see wetted grain boundaries also in this system. So you might get a peak here in this system while you don't get it in this system because your aspect ratios are too large, essentially. And here you have lower aspect ratios. That the wetness here of these higher temperature samples is more similar to what we see in the olivine plus basalt system. So, all right, rheology, melt. So this was the discussion earlier after Yasuko's talk. So the first % of melt has a quite dramatic effect. That's captured by that model. Has a quite dramatic effect on the rheology. So these data are really melt-free data. These are nominally melt-free, where you have up to 1% of melt present. And that first % of melt, makes a dramatic difference in the strength of the aggregate. So that there's a bit of the data here are a bit mixed. But in terms of the melt-free, it's very clear that first % of melt has this very large effect that is captured here essentially in this model. So that's the normalized shear viscosity. So if 1 here corresponds to the viscosity or the rheology of this material, this pure melt-free material, then you step up to this enhanced rheology over the first 1% of melt at those kind of grain sizes, right? So that's that step that we can actually experimentally we think quite reasonably explain. Well, we didn't know about the theory when we did the experiments. So, but that's behind that, and yeah, it's the short circuit, and I'll come back to that, the question of the relative sizes of grain boundaries versus triple junctions. So another aspect I want to point out, so this A in the equation that Yasuko showed, here A at 2.3 is 20 degrees. This is contiguity here. She showed that figure as well. That's from her paper. So we measured a wetness that far exceeds the isotropic model, of course. So then also, if we look at the contiguity here on the left, it's a little bit scattered. Basically, again, dunite, that's the partially molten olivine, as a function of grain size. The fine grain materials have a contiguity consistent. So this is this parameter A in the equation here. That's the equation that she showed. Right. So they have, contiguity that are relatively large, but if you go to coarser grain sizes, of course, this A exceeds that what you would predict as an empirical function for the isotropic model. So then, if you calculate the normalized viscosity, the viscosity also drops much more quickly than predicted for the isotropic model. So the idealized model would have A of 2.5 for a dihedral angle, I think of 1 degree or something like that. But, if you want to go further with this parameter A, to capture the actual measured contiguities, you need much larger A's, right? So that, and then the question is of extrapolation to mantle grain sizes, whether that trend continues. So yeah, again, what I said earlier, the fine-grained aggregates, this is Herten, Colston, Mai et al., in a grain size of 10 micron or so in that area, they look very faceted, right? And so that's what we're saying, that if you go to coarser grain sizes, the faceting becomes much less pronounced. You see much more rounded grain surfaces rather than facets. Grain boundaries, briefly, TM observations. So the key, that's again a TM problem, of course, right? You're looking at this nanometer scale resolution. You have a sample that's, even if it's millimeter sized, it's a vast real estate that you can't ever explore, right? So that's a little bit the problem with the TEM, especially since you want to look at general high-angle grain boundaries. Those are the most numerous grain boundaries in a polycrystalline aggregate, right? Nothing special about them. And if you image them in the by high-resolution TM, so you can see lattice planes here, the 0, 1, 0 lattice planes. They're smooth. There's no evidence for steps or dislocation structures. They're structurally distinct. Right? There's this layer, but that's of the order of 1 nanometer, that doesn't have the grain interior structure. And as I'll show next, they're chemically enriched. One other point I want to make, so we're in need of doing more of this. These are some recent experiments that I won't mention further, where we doped the sol-gel olivine with titanium. The grain boundary structure is exactly the same. So again, you can see lattice fringes here on this side of the grain. You have about a 1 nanometer wide region in this particular image that does not have grain interior structure.
What temperature is that at?
This was run at 1250 degrees. So the key point I wanted to make with these images is this is a genuinely melt-free sample, and that's a sample with about 3% melt. So looking at the grain boundary structure, you can't tell a difference. So the grain boundaries in melt-free, grain boundaries in melt-free and wet and melt-bearing aggregates look the same. The structure is exactly the
Is
same.
that the temperature at which these images were taken, or the temperature?
No.
Around? What temperature were the images?
That's just room temperature. Yeah, so this is just room temperature images. And he quenched the material, take it out, prepare it, and so on. The interesting part also, so that the grain boundary structure is the same irrespective of whether you have melt or not. They're chemically enriched, the grain boundaries, relative to the grain interiors. Again, that's nothing new. So here for the titanium bearing, so if you dope the olivine, the grain interior, with titanium, the grain boundaries are also enriched in titanium. And that's work that goes back to '96 now. Drury and Fitzgerald looked at calcium, aluminum, and titanium. They're all enriched, so the green symbols here is grain interior. The red ones are grain boundary analysis. The grain boundaries are enriched in these incompatible elements. And that's, of course, Siraga and others, Dave Kolstad, is exactly the same. There's agreement on the chemically enriched nature of the grain boundaries. So, yeah, the last part I'd like to get to is melt distribution in natural rocks. So, we'd like to extrapolate the experiments, right, to grain sizes that we do at grain sizes of tens of microns, to grain sizes of millimeters or centimeters as we think they are in the mantle. So we look at these natural rocks, these natural analogs, olivine-rich troctolites or plagioclase dunites. The composition is roughly 80% olivine or more. Much of the remainder plagioclase with a bit of clinopyroxene and spinel. And these olivine-rich troctolites occur at mantle crust transition, both drilled from mid-ocean ridges and picked up at prototype massifs. The one that we are looking at is the Kura-Jakoniuch Massif in Bosnia-Herzegovina. It has very large outcrops of these very interesting rocks. So just in terms of their mantle origin, so a little bit of chemistry, olivine composition, typically the way people look at this is magnesium number, so the iron content in the olivine versus the nickel content. Mantle nickel content, so in ppm here, about 3,000 ppm, that's a mantle rock. And then down here you probably have cumulates, so still water, and then rum. They have somewhat lower magnesium numbers and nickel contents. These plagioclase dunites that we analyzed from this massif are very similar in their olivine composition to the prototypes, the spinel prototypes and the plagioclase prototypes that we pick up from the same massif. So based on that, we would argue that these are really mantle rocks, especially because of their high nickel contents. So it's beautiful when we first started looking at these. I mean, this really, so you have to get your eye in a little bit. This is a plane polarized light image. You can see the scale bar here now, that's 2 millimeters, so these are millimeter sized grains in these rocks. Of course, the big problem is that all of these rocks are altered, right? You can't pick up a rock like you make it in the lab. They're always altered. And you can see the olivine grains here, that's serpentine. You can see a few remnants of the original olivine grain, the rest is serpentine. But then interstitially, the geometry of what was plagioclase, of course now it's clay of some kind, the dark stuff here, that was former plagioclase, that is really interstitial, and that has geometries that are very similar to what we see in the experiments, right? So much as you can say that here. There's also CPX here, so one of the things we've done is created EBSD, whole thin section EBSD maps. That's with Seth Kuchenberg at Boston College. He has a very nice EBSD setup where we can actually map the entire thin section. And we've colored intentionally the clinopyroxene here red. And you can see that the clinopyroxene, is interstitial between the olivine grains, essentially wetting the grain boundaries of these olivine grains. And you go through that. So all that black stuff, as I said, is plagioclase, which is gone, so it's not in the EBSD map. And you can see the olivine, right, where it's green, that's olivine, the rest in between is serpentine, right? So they're altered, but still, I mean, you compare this to the images that you saw, you can see faceting here, you can see these, the melt is what was, we interpret as the former melt, I should say, of course it's plagioclase, it was plagioclase, penetrating on grain boundaries as well as the clinopyroxene. And it's interesting from EBSD, you can tell that these clinopyroxene, that's all one grain essentially. So you get, this grain is interconnected in 3 dimensions. It's the same orientation. It's very nice to see that in EBSD images. Here's another example. You can see these, what look like wetted grain boundaries, right? So the blue here, that's spinel. That spinel is less altered. The light blue here, there's a little bit of plagioclase left. Fresh enough so that it actually indexes, but you can see most of it, all this white stuff, the plagioclase is gone, of course. We did some experiments, right, to confirm this. So instead of quenching from high temperature, we equilibrated these at 1350 degrees for a week, and then cooled them slowly so that we start to get crystallization. So that the melt in here is a basalt that was designed to be in equilibrium with 4 phases at, I think, half a kilobars. And so with 4 phases at half a kilobar, so melt plus 4 phases, olivine, 2 pyroxenes, and plagioclase. So the composition is that of a regular mid-ocean ridge basalt, basically. Not with the full complement of trace elements, but basically all the major elements of a mid-ocean ridge basalt. So if you cool that slowly, you start to crystallize, first you start to crystallize OPX, then in this, kinetically, you should start to get CPX because the melt becomes enriched in calcium. So you go from orthopyroxene to clinopyroxene, and that's basically what we see. And that's exactly the same geometry, right? You can see the CPX that crystallized interstitially where there was melt at 1350 degrees C. By the time we get to 1180 degrees, we have CPX crystallized. And then this is actually plagioclase now, so it crystallizes to plagioclase, but you can't see that. You actually, kinetically, you have a problem. Plagioclase is the viscosity increases. And so this is nanocrystalline plagioclase if you look at it with the TEM. It's not proper large single crystal of plagioclase in the natural rocks. But quite interesting, right? So the pyroxene crystallizes first, and you can see that actually retreats from the grain boundaries. And if you compare that to these natural rocks, so it looks like there was a wetted grain boundary, but now during the cooling, and you cool this, I guess, fast enough that you retain these kind of same structures. You can see that's the CPX, that's the CPX, and what we cool in the lab here, that's what you see in these natural samples as well, that you have some retreat of the what was the interstitial melt at high temperatures from the grain boundaries. And of course, the plagioclase doesn't do that. So the plagioclase retains the original geometry because it crystallizes at lower temperature, where kinetically, basically, you don't do anything anymore to the microstructure, at least in the experiments. So, and you can see olivine crystallizing. You start to get rid of these. So here's a bit of pyroxene. The olivine also starts closing up these very thin inclusions. Of course, you also get a little bit of olivine crystallizing out of these. So interesting also, very briefly, microstructures. So we wanted to compare the microstructures, or the lattice preferred orientation, or crystallographic preferred orientation. A sample from room, actually, Marian Holness provided that to us. You can see very nice here. This is exactly the fabric you would expect from crystal settling. So olivine as a platelet settling, with the 010 axis vertically, and then you get these girdles of the two other, the A and the C axis. And still water, the problem is, of course, the samples become very coarse grained. So this fabric isn't as nice because we don't have enough grains in the thin section to actually, but here we have lots of grains. That's a very nice fabric. And these plagioclase dunites have a completely different fabric. So the maximum here of the C-axis, and then not much going on in the others. And the problem here we have a bit is also that we just don't have enough grains in the thin section. So you'd have to map multiple thin sections in order to get a decent fabric because of the large grain size. But it's a completely different fabric, and one that doesn't correspond to any known deformed fabric. Sorry, I should run. So still water, grain internal deformation here due to crystal settling, which you don't get in room. The plagioclase dunites are undeformed. So in comparison, even crystal settling produces significant grain internal deformation indicated by the colors. But here for the plagioclase dunites, there's almost no grain internal deformation. They look more like, so if you look at this experimentally, they look more like a hot-pressed sample where you have coalescence of grain rather than a deformed sample where you have lots of grain internal deformation. So these samples are relatively undeformed. All right, so that's, yeah, summary. Sorry, running a bit over here. That's it. Thank you.
Quick question? Yeah, I'd like to comment just about this percolation threshold issue.
Yeah.
The only system that I know of where there was a true percolation threshold where you can prove, rigorously that below the threshold there's no conductivity, what is an infinite, say, for example, an infinite lattice. Then in that situation, for like the two-dimensional square lattice below 50%, you can rigorously prove that the conductivity is 0, the probability of finding an infinite pathway is 0.
Right.
However, as soon as you go to just a finite version of this idealized system, you can go to a melt fraction, volume fraction down to 10 to the minus 20th.
Right.
You'll still have a positive conductivity because of finite volume effects. There's still a non-zero probability that there will be a pathway through there.
Right.
The application of percolation theory to real material, there's always some sort of modeling, and even in the sea ice case, we see similar. In other words, is there a rigorous percolation threshold? Of course not. There's some degree of conductivity and so on, which is what Wen-Lu is seeing as well. And so I just wanted to make clear that this shouldn't be taken so seriously as a rigorous mathematical theorem, but it's a model which gets at the heart of the phenomenon and is phenomenologically very useful.
Right.
The real issue is, do you the minimal size, do they percolate? In other words, you have tubes such that they're large enough so that you see macroscopic effects of this, and do those percolate in some sense? That's really in some sense, a more relevant issue.
Yeah.
But so in any way, there's no real rigorous percolation threshold in any of these kind of materials.
Now, I take the point that what I'd like to say with the surface energies, that there are no conductances missing. So you have a perfect network. The question that was raising, what is the conductance of the individual network? And then you have different sizes, right? So the percolation threshold in that sense is when do you have enough large ones that you have high conductivity, but you always have the small ones, right? So
and even in sea ice, we see if we could increase the resolution of our X-ray tomography, and it also depends on the scale at which you're looking. The larger the box, the harder it is going to be to cross. And so there's always these issues that arise in applying a rigorous mathematical theory to a real material.
Right.
Okay, I think for the sake of time, we should just push on. Hopefully, have time for a conversation, especially since we need to take the time to set up the next presentation. Let's thank Uli one more time.